all an indefinite integral is a backwards derivative. So the things we've looked at so far are called definite integrals because they're the area under the curve of a function from A to B. So a definite integral has an upper and lower bound, and it's a number. An indefinite integral, which we normally are just going to call an integral now, is the exact same thing as an antiderivative. The difference in notation is just that you don't have an upper and lower bound. So if you just see the S integral symbol with a function, I'm just telling you, hey, here's a function. Tell me a function whose derivative is this function. See, it's literally just a backwards derivative. It's not a number. And since we don't really have any fancy techniques yet for computing antiderivatives like we do with derivatives going forwards, I'm basically just going to show you a couple tricks and things you'll see for doing these type of problems. So for example, all I'm asking you here, since you don't see a little a and a b, is tell me a function whose derivative is 1 over the square root of 1 minus x squared. So don't think, when you see these, don't think like quotient rule. There's no such thing as a backwards quotient rule. Don't think like substitution rule or any other advanced Calc 2 technique you may have heard of for whatever reason. You can do this just by looking at it. You know a function whose derivative is 1 over the square root of 1 minus x squared. At least you should know it. It looks like one of the weird inverse trig derivatives, right? And in fact it is. So you look up your table real quick and you're like, oh, right. The derivative of arcsine of x is 1 over the square root of 1 minus x squared. So that's the answer. So you see what I'm saying? The answer is a function. It's not a number. There's no upper and lower bounds here. I'm just asking you to do a derivative backwards. And so it's arcsine of x plus c. I'm just putting the plus c in for etiquette because it could be plus 100 or whatever. Again, there's no quotient rule. You can only do this because you can use algebra to split up this function. So the function x squared plus the square root of x plus 1 over x cubed, in this case, this is called the integrand. And the only reason you can do this is because you can use algebra to split up the integrand into 3 different things, and then you can take the antiderivative of those 3 different things separately. So most of the work here isn't calculus, it's just algebra. You're going to use algebra to pull this thing apart, and I'd say simplify, it doesn't really make it simpler, so that you can look at all your individual summands separately and integrate them. If you have a common denominator between fractions, you can add or subtract the fractions together, so that works both ways. So this only works because you only have one thing in the denominator. You couldn't do this if it were the other way around. Since you have one thing in the denominator, you can pull that apart into x squared over x cubed plus x to the 1/2 over x cubed plus 1 over x cubed. Right, we're writing square root of x as x to the 1/2 so we can use the powers. So just convince yourself that that works backwards, right? That's not calculus. That's just algebra. We didn't do any integrating yet. Now we just use the rules of exponents to simplify those 3 separate terms. Anytime you have like 3 separate summands inside your integral, you just do them term by term, just like a derivative. So x squared over x cubed is 1 over x. X to the 1/2 over x cubed is, remember, you subtract the exponent, so 1/2 minus 6/2 is negative 5/2. And then 1 over x cubed, you're just going to write as x to the negative 3. And now, okay, so you can use the power rule or the backwards power rule on the x to the negative 5/2 and the x to the negative 3. And then the 1 over x, you know that you also have a trick for. That was calculus, right? Everything up to now is algebra. The algebra is almost the harder part here. That move was calculus. So the antiderivative of 1 over x is natural log of the absolute value of x. The antiderivative of x to the negative 5/2, okay, power rule, 5/2 plus 1 is, I'm sorry, negative 5/2 plus 1 is negative 3/2. And then you also know you have to divide by -3/2. -3 plus 1 is -2, so it's x to the -2 over -2. And then I threw in a plus c just again for etiquette. If you left the answer like that, I wouldn't mark it wrong. I just personally don't like to see compound fractions. That over -3/2 is gross to me. So I'm going to simplify it just a little bit. So I'm going to rewrite that as natural log of the absolute value of x minus 2/3 x to the -3/2. You probably could have done that step in your head. Instead of saying over -3/2, just say minus 2/3 x to the -3/2. And then I'm just going to rewrite that as minus 1/2 x to the -2 plus c. You could simplify it even more by like putting the x's in the denominator and stuff, but I would say this is as far as you should go. This is a fine answer. I like this just fine. So, the only real way to check this is just to do what you just did backwards. Take the derivative of the thing that you're looking at, and then you'll see that it does combine into the original function. But again, this is a specific case. You're not just going to be able to take any rational function and integrate it. In fact, in a lot of cases, it's impossible. In many cases, it's just so hard that only really a computer could do it. In some cases, you can do it by hand, and you will in Calc 2, but I'm telling you, it's a giant pain, and it's called partial fraction expansion, and you're just going to hate it. So this is, again, the things I'm showing you today are specific cases where we have a trick, where we can do it just by hand. Another trick is a trig identity. So if you look at this, you don't have a basic function whose derivative is tangent squared. And again, don't think product rule or chain rule, because there's no such thing anymore. You don't even really have a basic function whose derivative is tangent. We haven't even seen that yet. So you certainly don't have one that's tangent squared. This only works, you can only do this because of the following trig identity. Tangent squared is secant squared minus 1. Maybe you didn't remember that exactly off the top of your head, but you should know that there was a trig identity relating tangent squared and secant squared. It's one of the three basic, what we call Pythagorean identities of trig. So tangent squared plus 1 equals secant squared, or tangent squared equals secant squared minus 1. That only works because we just so happen to have antiderivatives for secant squared and for 1. So again, no calculus has been done. We haven't done any calculus yet. We just used a trig identity to replace the integrand with something else. And again, it just so happens that in this case, we can integrate these two things. So think about it. What's a function whose derivative is secant squared? And what's a function whose derivative is 1? You know both those things. The derivative of tangent is secant squared, and the derivative of x is 1. That one screws people up. When you integrate, things like the minus 1 don't go away. You're looking for a function whose derivative is 1. That function is just x. So that's it. That's the answer. And I know it looks weird, like really the derivative of tangent of x minus x is tangent squared? Yeah, through some trig stuff. Right, so really those are the only tools in your toolbox for now. Use algebra to rewrite something, or use trig to rewrite something as something you know how to integrate. One more thing we can do with indefinite integrals is I can tell you a fancy integration formula from Calc 2, and I can just ask you to check that it works. And how do you check that it works? Well, an integral is a derivative backwards. So you take the derivative of the big crazy thing that I'm telling you that this is the integral of. Here's what I mean. I'm just telling you that the integral of the arctangent function is x times arctan of x minus 1/2 natural log of x squared plus 1 plus c. I'm not asking you to do that. To do that involves something by integration by parts. If you know how to do that, great. I can't fault you for that. It's awesome. You'll do it. It's not that hard. You'll do it in Calc 2. But that's Calc 2. So when I say verify the formula, I'm just asking you to convince me that the derivative of that thing on the right-hand side is just arctangent. So I'm just saying check. I know it doesn't look right, but it is. Check that the derivative of x times arctangent of x minus 1/2 natural log of x squared plus 1 plus c is just arctan. It doesn't look like it is, but it is. And so that's what I mean by verify. Don't do it. Don't do the integration. Just do the differentiation and see that it simplifies. It does. Here we go. Okay, so the derivative of x times arctangent of x involves the product rule, and the derivative of 1/2 natural log of x squared plus 1 involves the chain rule. So that first term is going to be, okay, x times the derivative of arctangent of x plus the derivative of x times arctangent minus 1/2 1 over x squared plus 1 times the derivative of x squared plus 1. So we're using the product rule and the chain rule. So you can't forget your derivative rules. They never go away. So there's all that. So it's x times the derivative of arctan, which is 1 over x squared plus 1, plus the derivative of x, which is just 1 times arctan, minus 1/2 times, all right, the derivative of natural log is 1 over, so it's 1 over x squared plus 1, and then by the chain rule times the derivative of x squared plus 1, which is 2x. So it doesn't look good yet, but you have to do a little bit of algebra to clean it up. So again, the calculus is over, right? And now it's just algebra. So that first term you can just write as x over x squared plus 1. That second term is just arctangent. And that third term, the 2's cancel out. So you can just write that as minus x over x squared plus 1. And the c went away in the first place, right? Because we're differentiating. So hey, look at what you have. The first term and the third term cancel each other out. And lo and behold, it's right. So I'm not going to ask you to verify a formula that's not true. If you get an answer that's not just arctangent, you did something wrong, right? I'm not trying to trick you. I'm just, again, telling you a formula that you'll figure out by yourself later in Calc 2 and just saying, check for me that this works. And all I mean is just by taking the derivative of the right-hand side. So there's all these kind of formulas like the integral for natural log and the integral for arcsine that when you first look at it, you're like, that can't be right. But it is by the properties of things like the product rule and the chain rule. You'll just have to take my word for it.